we're still exploring how Cauchy's theorem, a theorem about integrals, including the representation theorem, tells us about the local behavior of an analytic function. And what we're actually aiming at here is something rather elementary, which would be worth reviewing in order to see what it is that we're aiming at. And so here's a situation that you might have bumped into in calculus or even pre-calculus, which is to graph this rational function. The top is x minus 1, and the bottom comes to you factored x plus 2 times x minus 3. And the trick that you might have learned, I don't think it's universally taught, but I really think it should be, is that we look near the three important points. We've got a 0 at 1, and the function is not defined at minus 2 and at 3. And so we look around those 3 points and we say, you know, like for example, when x is near 3, then x minus 1 is not 0, and x plus 2 is not 0. And so if we can make the following conclusion: if x is near 3, then y is near, now I'm using pre-calculus talk, we should be saying this in terms of limits, but you're sophisticated enough that we don't need to necessarily go into that much. Well, let's see. If x is near 3, on the top here, the top of y is near 2, and on the bottom, x plus 2 is near 5, and x minus 3 is, well, we can't plug in 3. That's what we're doing. We're plugging in 3, and we're saying, well, that actually happens in a neighborhood. Oh, sorry, I'm doing complex analysis. That actually happens in a neighborhood around 3. So, so what we do is we get a pretty good handle on the local behavior of y near 3, and it's a shifted and scaled graph of 1 over x. And so we can make a little local graph like this that we know 1 over x is the hyperbola. And so what we can say is that y looks like this near 3. And if we do the same kind of thing at 2, we find, oh, I'm sorry, we don't want to do it at 2. We can do it at 2, but you're not going to find anything interesting. If you do it near minus 2 is one of the places where the function is not defined, then what you find is that y is near, I'm just going to do this in my head, on top minus 3, and on bottom minus 5 times x plus 2. So again, that's another stretched and shifted y equals 1 over x graph. So we know what that looks like. And so I'll just draw that in. This is near minus 2. And it's exactly the same picture as before. I'm conveniently skipping the scales. We're getting the shapes here. And then if we look near what happens, near 1. 1 is the place where the top vanishes. So near 1, y is near, well, on the top we're going to have x minus 1. You can't plug 1 in, you won't find anything interesting. And on the bottom we'll have 3 times minus 2. And so that means that near 1, the graph looks like a shifted and stretched y equals negative x. So the bottom here is negative. And so that's just a line sloping down. And so I'll just draw a quick little cartoon graph of that. And there it is. So this is what happens at 1. And the idea in calculus or pre-calculus was to put these local pictures together to come up with the global picture. And this is a very, very powerful tool. So we have asymptotes at minus 2 and at 3. There's a horizontal asymptote of y equals 0. I didn't go into that, but you noticed it anyway. And then I start filling in the local pictures. And so near 3, where right now I just have a template, near 3, we know the graph looks like this. I'm leaving some stuff to be filled in later. And near minus 2, we're getting the same picture. And then at 1, which is someplace in between, that's the 0. Well, the graph has to go through that with a negative slope, and ta-da, we've graphed this rational function, doing very, very little work except taking advantage of that local picture. And so the local picture is something that we can do now with arbitrary analytic functions. With arbitrary analytic functions, the big tool is Cauchy's theorem, and we're just going to be able to do this kind of analysis. Now, of course, we're not graphing these things. We're much too sophisticated for that now. We have to drink with our pinkies up. We want to do more sophisticated things than graphing. And, graphing is never the solution to any problem. It's an aid to finding the solution. So, but now our graphs are in 4 space. And so this is getting to be, pardon me, my dog's saying hi. This is getting, hi, Sammy. She's a very analytic dog, let me tell you. Okay, so what we're going to this depends on is this Taylor-like expansion that we've already talked about. So we're going to talk about f of z, and we're going to say this is the sum j equals 0 through n minus 1 of the terms that you would normally see in the Taylor expansion. So those are fractions. You get the jth derivative of f evaluated at a. Remember, a is the removable singularity on top, and then j factorial on the bottom, and then z minus a to the j. So we've started out like we're doing a Taylor expansion, but we're going to stop. That's enough of that, and we're going to throw in this f sub n of z times z minus a to the n. And let me just throw in a reminder that a is removable singularity. And so that's the kind of thing that we've bumped into before. And we know that for removable singularity, Cauchy's theorem about the vanishing of integrals, the function's not analytic at a, but it's got this removable singularity, and Cauchy's theorem still holds for that function. And we did that with the difference quotient, which enabled us to find the following estimate. This is also based on the Cauchy representation of the nth derivative. What you find here is that f sub n of z is 1 over 2 pi I. No one has come up with a good single symbol for 1 over 2 pi I. Integral over c. C is the circle around the removable singularity of a fraction. And the top is traditionally f of zeta d zeta. So zeta is a variable that's going around the circle. And on the bottom, we've got zeta minus a to the n times zeta minus c. So this is a funny expression because a appears in the integral, that's our removable singularity, and z, the thing we're calculating the value of the function at z is, well, it's in there way kind of hidden in the fine print on the bottom there, and then zeta is the parameter around the circle. So so there's the deal. So there's this representation of f, and to make a long story short, it's there's a crude estimate for this, which enables us to do something that Alfors does not quite emphasize enough for my taste, which is the following. That is, if f is analytic, and then it has no zeros of infinite order. So that means the order of a zero, well, if the function vanishes, is order 0. If the derivative also vanishes, order 1. If the second derivative also vanishes, it's order 2, and so forth and so on. And you can't keep doing that forever. And so that's the deal. And there's a very nice removable singularity trick to this that depends on this Taylor expansion. And so what you end up doing is you say, well, wait a second. If f had zeros of every order, then I could do this Taylor-like expansion for every n. And so that means for every n, you get that f of z is f sub n of z times z minus a to the n. Well, now we apply this very crude estimate. I'm going to leave the details to Alfors. But you apply this very crude estimate saying, well, we're on a circle of radius r. So what happens to this integral, and we remember we're multiplying it by z minus a to the n, what happens to this integral right in the center when you integrate over the circle? Well, the circle has a radius, let's call it capital R. And so you get this very crude estimate. And what that shows is that the absolute value of f of z is in fact 0. You can do this for every n, so you do it for bigger n, bigger n, bigger n, bigger n, and when you get this crude estimate, you find out that the whole thing is going to 0. So you have something less than 1 raised to the nth power. Okay, this can be extended to the whole domain of the analytic function f based on a connectedness argument that I'm going to skip over for now. But basically, remember, a connected set can't be partitioned into two open sets, and the set of places where f has a 0 and infinite order is open. That's what we just showed. And the set where it doesn't have infinite order is open. That's because you can take a neighborhood where something's non-zero. So you have these exclusive, mutually exclusive conditions, and that might put you in one open set or the other open set. So we've partitioned the domain, and that can't be. So either one of those conditions has to hold, and so you just can use this to determine that there's we can't have an infinite number of zeros in the whole region. You start with one disk and it extends out to the whole domain. This is a very complex analytic kind of thought where things can kind of spread out. That's this, you start with something local and it spreads. Whoa, okay. So let me run one other definition by you. And so first of all, what we're doing here is we're finding some h where f of z is expressed as z minus a to the h times f sub h of z. We've seen this again now several times. This is for removable singularity a, and you look at the smallest h where it doesn't vanish. So that means that this f sub h is analytic and non-zero. Well, isn't that what we were doing up here? We were saying, well, it's not 0, and in the real case, you can pay attention to the sign, the SIGN, and so that gave us these little cartoon graphs that we were able to put together into a good graph of the whole thing. And so we've got the other factors here. These are like the f sub h's. H would be 1 in this case. They're analytic and they're non-zero, so if the value's 1 over minus 6 at a, then that's non-zero in a neighborhood of a, and so that's by continuity, and so you can't, that would be a jump if you could do that, and so so there's the deal. So there's another definition that's very important that follows from this, and again we're going to see the importance of this removable singularity condition. So suppose we have that the limit for z near a, I'm still going to insist on z is near something. It doesn't go anywhere. It's not going anywhere. It's just near. Suppose that limit is infinite. Now, one of the things that we do, because we know about stereographic projection and we know there is a point somewhere on the Riemann sphere that corresponds to infinity, we can just write f of a equals infinity. If you do this in calculus class, you probably get slapped with a wet noodle, but we're not in calculus, we're in complex analysis. We've got stereographic projection, and infinity is just the North Pole. So that's a legitimate thing here, and so we'll take advantage of it. Now, if this is the case, if f is near infinity, then f is not near 0. So, so f is non-zero in a neighborhood of a. Remember, a is, well, it is what it is right now. And so what we're going to do is just turn the whole thing upside down, and we're going to define a new function, g of z, to be very simply a fraction, the reciprocal of f of z, 1 on top, f on the bottom. So that's kind of our situation right here, if I can get my hand out of the way. Now, g is not defined at a, because f of a is infinity, but that's a removable singularity. And so that means that the function g extends to have a value at a, and in fact, that value is 0. So g is undefined at a, but it extends to a because it's a removable singularity. And g of a is in fact 0. Now that 0 has an order, and so we can use with that. In this situation, what we have is that a is called a pole. And the order of the 0 of g at a is called the order of the pole. That's a pretty orderly definition. And so what we're going to have to do, using, again, actually rather elementary tools from Calculus 1, is explore the interplay between zeros and poles in the local behavior of a function. And again, this removable singularity thing, this is a very, very powerful tool, and so we have taken good advantage of it.